Our next speaker is Ari Silburt from the University of Toronto, and he's going to tell us about recalculating the frequency of Earth-sized planets.
Thanks, guys. So first I just wanted to point out my collaborators on this work, Eric Guidus and Yanshin Wu. They were invaluable to help me out, and I could not have done without them for sure. This work is based on the paper abstract, link is down below. I'm going to skip through a lot of the methodology and just kind of give the brief overview because it's only 10 minutes. So, let's start. So, since the dawn of human recorded history, people have looked up at the stars and wondered, are there other planets like our own out there? And so for a long time we've been grappling with this kind of question, and only in recent years have we gained any ground on this kind of answer. So mainly the Kepler Space Telescope has been invaluable for detecting planets outside of our solar system, but unfortunately there are very few, we don't have a true Earth analog yet that we've detected. There are many planets that you can argue are habitable and such, but the true Earth-like analog does not actually exist. This is an old plot, but it's still true today. So we have to infer this value, and the way that we infer it via Kepler is you stare at a patch of sky, count how many planets you detect, and then you try and correct for the ones that you think are out there statistically, but we don't actually see. So there are two main corrections that you have to do. The first is a geometric bias, which is fairly straightforward. Essentially, for every planet that is transiting, there was a certain probability that it did not transit based on the orientation of the system. And so for every planet you detect, you scale up that value by A over R star. And so that's fairly straightforward. Detection bias is a little bit more complicated, which essentially assumes, given that a planet is transiting, what's the probability that we'll actually detect it? And so one could naively, it's intuitive that smaller planets are harder to detect, larger planets are easier to detect, sorry. So here's a plot of completeness, or the detectability of planets. So the y-axis is the radius of the planet, the x-axis is period. Blue essentially means it's very, very hard to detect, essentially 0. White means it's very, very easy to detect. And so you could have a talk about this for probably a whole hour if you wanted to. The main point that I want to point out is that completeness is a very, very steep function of planetary radius. So if I, for instance, started this box here, 1 Earth radii, between 1 and 1.4, completeness or detectability is about 13%. If we even move up just 2 spaces in log, up to 2 to 2.8, it's already jumped from 13% to 86%. And if we want to understand the occurrence of planets, we really need to get that right. Coupled with this fact that completeness or detectability is a strong function of radius, the Kepler sample is very, very rife with errors. So I just scrolled to a random spot in the NASA Exoplanet archive, and just in this random spot there were 3 planets whose error bars are over 50% of the actual quoted value. And in one case, this error bar is actually larger than the actual value itself. So this is maybe many people are aware of it, maybe not, but errors are very rife in the Kepler data, and the main place that this is stemming from is the stars. So we don't understand the stars very well. There are a couple of people who also have talked about this fact, and I can't remember her name, but shout out for spreading the gospel, because this is the main problem for why we don't have better grasps on the true values of our radii. So many analyses in the past have neglected to account for this fact. So maybe the most famous analysis is by Pettigura, and so these error bars represent Poisson errors, which are essentially errors based on the number of counts in this bin, but it doesn't account for the fact that maybe a planet that is included in this bin could actually be part of another bin. And because the errors are so significant, there's a non-zero probability that this planet, which is 3 times the size of Earth, could actually maybe be Earth-sized within error bars, or it could be maybe larger than Neptune within error bars, even a 1 sigma error bar. So this is definitely something that is important to try and find a remedy for this. So this is the basic analysis that we decided to do. I know that Dan Foreman-Mackey, who's somewhere here, also has another analysis, and they tried a slightly different approach, maybe on Bayesian analysis, but I'll show you what we did. So basically what we did is start off by creating a probability distribution which is centered around the true value, 1.52, and has a Gaussian distribution, and it has the sigma based on the uncertainty. Then what we do is we essentially sample this very finely, maybe 5,000 samples, and for each sample value, for each radius value, we multiply that by the completeness value, which kind of makes sense because, let's say, according to this probability distribution, a Jupiter-sized planet, maybe over here, has the same probability of being that true value as an asteroid. But we know from the Kepler data that Kepler would have it would be impossible to detect an asteroid, whereas it would have a very easy time to detect a Jupiter planet. So we have additional information we can put into this probability distribution. So when we apply this information to those Gaussian distributions, we end up with things that look more like this. Ignore the dotted line, just look at the solid. So the solid red line is that true value again, and you can see now that this probability distribution has shifted. The quoted value from the Kepler distribution, from the Kepler website, is no longer the most probable value. And this essentially stems from the fact that all things being equal, if a given planet has large error bars, it's more likely to be a larger planet than a smaller planet, because smaller planets are harder to detect. So when we plug in this information and calculate what's the occurrence of planets, we get the following plot. It's super busy, but I'm going to break it down for you guys. So you can start off by ignoring this blue one. The red and the black lines essentially represent our main results accounting for these error distributions. And we use two different analyses, an iterative simulation and an MCMC, just for consistency to see that it's not method dependent. And then this green line here represents what we would have gotten if we did not include these incorporating these error bars into our analysis. And so you can see that these results are most sensitive at the small planets, where we're most interested, at the Earth-like planets. And so this essentially stems from the fact that, so let's say in one of these bins, there's very few planets, maybe only 8 or 9 planets fall into this bin. And so if we use our error distribution, which shifts maybe half of those planets away, then that essentially decreases our occurrence of planets by about half or something like that. So as a result, we calculate much, much less planets. This blue line is essentially, there have been a lot of studies that have suggested that Kepler-Stars are actually a lot larger than we think that they are. And so this essentially assumes that the stars in the Kepler sample are about 25% larger. Now that's probably a little bit of an extreme example, but this just gives you a rough estimate of how the distribution would change as we figure out if the stars are actually larger or smaller, etc. So, in conclusion, the calculation, the eta Earth that we calculate, the frequency of planets in the Kepler sample is about 6.4%. This value would have jumped up to about 10 or 11% if we had not included the error bars in our analysis. Radius error significantly affect this calculation, which some analyses have not taken into account. These analyses obviously have many other strengths, which I don't have time to talk about. But I definitely want to stress that this analysis is definitely a pass job. I'm the first one to admit that this is not like the answer. Obviously, there's a lot of work to be done to understand what this is. It's more just a proof of concept that shows how things can change if you include these error bars, which are pretty important just because they're so large. But hopefully Gaia is an instrument which is claiming to reduce these error bars and get high precision values of these stars, and so hopefully that should reduce these error bars and get better measurements. Thank you.
Plenty of time for questions.
We know that most of those stars are also binary, so most of those transits are dilated, leading to increased effective depth normally. So that would lower that number further, wouldn't it?
Yes, it would, yeah. So I'm basically just, as I said before, I'm not claiming that this is like the absolute value. I'm just showing if I assume that all the planets in the Kepler catalog are what they say that they are, then what kind of answer do we get in the end? Yeah.
So in this type of analysis, you first calculate completeness, and then of course it will be more complete for smaller planet, and then you include analysis for this Gaussian and a skew for a larger planet. It seems to me that you penalize the detection of smaller planet twice, and that's the reason why you get a lower number for eta Earth. So is that reasonable?
Yeah, I think so. So I think the first part, the completeness part, essentially, regardless, the way I calculate completeness is essentially I assume a value for the stars, and then I throw trial planets, not even real Kepler planets, just trial planets around these stars to figure out if I have a one Earth-sized planet, what's the probability that I'll detect that planet in my Kepler sample. And then I use the information of, so given that this actual Kepler planet could be an Earth-like planet, or maybe it could be twice an Earth-like planet, then what's the likelihood, how does this contribute to the occurrence of planets given that I'm not really sure what the true value is? So we could talk a little bit more about it later, but in the end I don't think that I'm double counting this information.
How well do we know the errors in the stellar parameters, and are they Gaussian, and if not, what do we need to do to understand those errors?
Right, so essentially the biggest problem for these error bars is a lot of the Kepler-Stars are based off of photometric measurements, and so those are very sloppy. Well, I guess you can do better precision. So if you did spectrophotometry and astroseismology and all these other things, so I guess I'm not an expert in astroseismology, but my guess is it's hard to get that kind of precision using that technique for stars that are very far away. So that's kind of an unfortunate situation about the Kepler population because they're so far away that doing hardcore follow-up is harder to do. But I think that if you could get spectral measurements on all of these stars, then that would go a long way. I think the main problem comes from the fact that the radius is derived from the log g values, and the log g is not very constrained from the Kepler measurements.
How would you know that the rest
Can you speak up?
How would you know, do you know a priori that true radius and your nominal radius, the difference between that is normally distributed as opposed to some other weird?
Yep, that's a really good question. It was more for convenience that Gaussians are much easier to deal with. Usually in any kind of astronomy or scientific thing, you assume a Gaussian distribution. But I'm not saying that that's right. It could very much be wrong, but I have no reason to believe that it should be something in particular, and so I might as well assume something that's very well understood, unless I had additional information that would tell me that it's something else.
How do you think that you could know from the way you face
Maybe we'll talk about how, yeah.
One last question.
Do you plan to redo this analysis once all the Q17 data has been analyzed? You know, some of the reporters' data are there, and they do have improved error bars on the radii.
Yeah, absolutely. It would certainly be, I mean, my whole pipeline is all set up just sitting in my garage, so it'd be easy enough, I guess, to just use a new data set and just pump it through. So, yeah, I might do a reanalysis when all the final reports come out.
All right. Let's thank Ari again.